Hello friends, I welcome you all to this session on C++ programming. So in the previous lecture, I have discussed with you about a problem that is fluid is flowing between two parallel plates and the flow is perfectly laminar, and it was expected that we should be in a position to find out the velocity variation along the height of this particular channel. Now the equations primarily used for evaluating this are Navier-Stokes equation, and when imposed to appropriate constraint, then that becomes ordinary differential equation. And this with a boundary condition that when you are at the plates, that means y is equal to 0 and y is equal to h, the velocity is 0. Then what you can do is you can discretize this particular equation and you will be getting this answer. This we have discussed. Also, I have told you that this is the exact numerical, exact analytical answer for the same problem. So, we will be comparing our result with this particular analytical result to see that whether we are correct or not. So, what was our task? Our task is to create one class. The class name will be channel flow. Channel flow is the name of the class. And what we do is, as I have not discussed with you about the templates, specifically the vector, so what we'll do is we will make our ordinary arrays, and beforehand we will fix the number of data points. The number of data point means that how many points we want in this domain from 0 to h. So that number is depending on totally on you. So I can start with lesser number of points. Let's say I'm taking only 10 number of points, so that the 0th and the 9th index will be my boundary condition. Okay. Okay, then you will be having some data members. So the height of the channel, viscosity, the tolerance limit, along with the exact or no exact analytical value or numerical value, sorry, for u array basically, and array for exact u, and then the array for y, as well as the dy, that is the spacing between two nodes. If you look here, this spacing is dy or delta y. Okay, so these will be my data members, and then my member function will be first the constructor. Now inside the constructor I will be doing so many things. Constructor, this will be parameterized constructor. This will be accepting h, mu, tolerance, as well as, oh, there is one more thing missing, that is dp dx, which is a very important thing. So dp dx, that is the pressure gradient in the x direction. So this will also be there, and then I will be creating a constructor which will be accepting this, dp dx and epsilon. That's it. Once this is done, inside I will be assigning to the appropriate values, appropriate variables, and then inside the constructor itself what I will be doing is I will be evaluating what is dy, and also I will be initializing the exact value of u as well as the numerical value of u with a value 0. This is just the initial guess you can think, or just initial initialization. This is very much required because we want to solve numerically the problem. So while solving numerically, we should have some initial guess, some initial value. Then only this particular thing will work. Then once this is constructor is over, then we'll be creating boundary condition. That means when y is equal to 0, u is equal to 0, and when y is equal to h, u is equal to again 0. Once this is done, then we'll be writing a solver for the numerical problem, and that solver will be nothing but we'll be solving this particular equation node by node. And how that can be done? So if I focus here, let's say these are the only data points we are having. So for any ith location, I require what I plus 1 and I minus 1, as I is increasing in this direction. So for any ith location, I will, and this is the domain where the equation will be solved. So for any ith location, these will be required. Okay, very good. Then what we'll be doing is, previously we have taken one guess. This is the guess. I am saying 0. So the previous value can be taken as the guess. So what I'll do for any particular node, this I'll do. Then I will evaluate ui based on the equation. Which equation? Discretized equation, this one. Okay, based on this I'll be evaluating this. Then I will be doing what? I will be finding out the difference and then square it. for any node, and this thing will be done for all the nodes, for all the internal nodes, then summed up. Once this is sum, then taken square root of it, and that becomes what? Root mean square. So that is my error. So what I'll say, that if the root mean square value of this error is less than the tolerance criteria, what is the tolerance? Tolerance is nothing but this epsilon. You can take it 10 to the power minus 2, 10 to the power minus 3, minus 4, minus 5, depending on the accuracy you require. Okay, once this has been done, this is over. The solver is over. And then analytical solution, it is very simple, friends. This is just the equation. So let us directly jump to the code blocks and let us see how to write class for this. So first thing first, I am already having IO stream, then CMath I am having. Then let us create one class called as channel flow. Now, what are the private data members? So by default, you know, the data members are private. So if you don't write public, unless you write public, everything will be private there. So you needn't have to write private specifically. So let us say double. So h, that is the channel height, then mu, and then dp dx, okay, and then epsilon. What is this epsilon? This is the converging criteria, okay. Then the u, that is numerical u, that means the value of velocity which we will be getting after solving this equation, that is this discretized equation. Then your exact value of u, array for it, and having n elements. Then you will be also having y and then dy. So let's say these are my data members. Now for this I require this n. So what I do is I'll make it here const int n, and let's initialize this with 10. So 10 elements are there. Done. So this will work now. Okay. Now what I have to do is public now my member functions. The first function will be my constructor. Okay. So as I know that constructor is having the same name as that of the class, and it doesn't return anything. So now this is parameterized I am making. So let us say double, and h, let us say h is for height, okay, and double, and viscosity I am writing vis, and that will be assigned to mu, okay. Then double, then pressure gradient, and that will be assigned to dp dx, okay. And what else? Epsilon we can also give, okay. So let's say converging criteria, or EPS we can write, doesn't matter. Now inside, first the h will be assigned to this h will be assigned to this h, as C is case sensitive, C++ is case sensitive, so they will be treated as different. Okay, now mu will be taking the value of viscosity, okay. Then dp dx, this dp dx will be taking this pressure gradient, so this is nothing but pressure gradient, and this epsilon will be taking the value of EPS. Friends, this is over for the input part, but some calculation we will be doing here itself. What are those? Once I know this height, also I know the number of data points, I must be in a position to find out what is dy. Why we are doing this inside this particular constructor? Because we are constructing everything here, okay. So dy, what is dy? So if you look here, how many data points are there? 1, 2, 3, 4, 5. So for 5 data points, if the length is h, so total length is h, so what is the distance between two nodes? So this will be nothing but h divided by 5 minus 1, that is 4. 1, 2, 3, 4, isn't it? For n data point, it should be n minus 1. So that is what we will be doing here. So this dy will be equal to h by n minus 1. I think this is done. Once this is done, then we will be evaluating the y. That means if you look here, y here it is 0, it is dy, it is 2 dy, it is 3 dy, it is 4 dy, and 4 dy is nothing but h. So that is what we will be doing here. So for int I0, I less than n, I plus plus, oh, I have done something wrong, I plus plus, now it is okay. So what I will be doing is, my yi will be nothing but I times dy. So once this is done, then what you can do is, you can initialize the arrays for u and this, that is numerical and exact values as with 0. Okay, let me copy this, and inside what I will be writing, oh, thoda sa bahar. Okay, now inside what I will be doing is, ui will be equal to 0.0 as well as u exact I will be 0.0. So this is over, initialization is over, and we have uh, created this particular channel flow. Now constructor is done. Once constructor is done, then the next task is to write the solver. So what name I suggested here, it is numerical solve. Okay, then. So now let us write function for, this is for channel flow. Okay, this is for constructor only. Now void numerical solve. So what we will be doing inside this, we will be simply solving that particular numerical equation, that is this half ui plus 1 plus ui minus 1 minus this, and we will be continuously doing it till the convergence is reached. So how that can be done? This is simple Gauss Seidel. If you are having difficulty in understanding Gauss Seidel, then what I'll do, I'll leave one link in the description of this video, so you can also watch that video. Now what we'll do is, we'll create one variable error, because that is the one which has to be reduced, and initialize it with some big value, let's say 1. Then we'll also make one counter for basically knowing that how many iterations the program has taken. Then while the error ERROR, while the error is more than what? Error is more than the converging criteria, that is epsilon. What we have to do? We have to do something. Okay. So what we'll do, we'll create one variable for summing up the errors for individual nodes, that is this particular thing. So double s and assign 0 to it. Now once this is done, then we'll run a loop for finding out the value of ui, for evaluating the difference of guess as well as ui. So for int I, now again you have to be cautious. The loop can only be done in for inner nodes, not for the boundary nodes. For boundary nodes, we must be having some boundary condition, which I have not created. I will create it later on. Okay. So now, or let us do what? Let us create the boundary condition first. So void boundary condition, and that is nothing. That is the 0th value of u is 0, as well as the last value. So as index is starting from 0, so the last will be n minus 1, and this will also be 0. Done. Okay, now here starting with 1, and then I is less than n minus 1 and I plus plus, because we have to iterate in the inner nodes only, for the inner nodes only. Okay, and inside what we will do is, we will create one u guess variable and assign this with ui. Why? Because we have to find out the evaluated value minus previous value. So previous value will become my ug. Now I will evaluate new value for ui. So what is that? It was 1 by 2, or I can write 0.5 here, 0.5 times. So if you look here, it is ui plus 1 plus ui minus 1. Okay, so it is u I plus 1 plus u I minus 1, and then minus dy square, if I am not wrong, let me check it once more. So it is dy square, so it should be d. So dy square divided by mu. Okay, look here, dy square by mu and then dp by dx. Okay, and then finally this will be multiplied by dp dx. Done. Equation is also solved. Then you have to find out the difference. Okay, of what? U guess minus ui. This difference, you square it up, that is POW. You square this difference, okay, or you can also write one bracket here for extra precaution. Okay, now you have done what? You have squared that difference, and now you will be adding for every node and then transferring it to S, or you are adding in the S, the same thing. So S plus assign this value and closing the statements. Once this has been done for all the nodes, let us bring this out. For all the node, once this is being done, then we will be evaluating the error for that particular iteration. So error will be equal to square root of this S. That's it. Very simple. Then once this has been done, what we have to do? We have to update the boundary condition. So boundary condition already we have created this, and we now have updated them. It is very simple. Then once this has been also done, then you simply increase the count. So count plus assign 1. That's it. After this, this is your while loop and this is basically your okay. So now once the program converges, then your function, this function, numerical solve function, should tell that how many iterations the program has taken. So total iterations is equal to so I should start with 1, let's say 0, not 1. So total iterations will be equal to count and then endl. Okay, done. So your numerical portion is also over. Then once numerical portion is done, then what you have to do is you have to write for the analytical portion, and it is very easy. Look here. So void and then analytical solve. Okay, and inside you will be running a loop for int I0 and then I less than n I plus plus. What you have to do? You have to simply evaluate the values of exact. That means u exact is 1 by 2 mu minus dp by dx h minus, and this will become I yi for ith node, and then finally multiplied by yi. So let us write it. So this is equal to u exact I, and that will be equal to 1 divided by, it was 2 mu, 1 divided by 2 mu, and this whole will be multiplied by dp dx, dp dx minus dp dx, okay, and then that will be multiplied by h minus yi, remember. So it is, oh, what I have done, so it is h minus y ith value, and then finally multiplied by yi. That's it, simple. Now you have your analytical result also. Once you have your analytical, let us create one more. Have I done something wrong? Yes, it should be inside the class itself. So it is inside the class. Just bring it. Okay. Now finally we'll do what? We'll create one more function for displaying the result. Void result display, disp. Yeah. Okay, doesn't matter. Now inside, for first what I'll do is, because I have to transfer the data to the Excel to show you that whether it comes parabolic or whether the numerical and the analytical results matches or not. So what I'll do, first I'll print y, then I will print numerical values, and then I will print exact values. Okay, so for int I0 I less than n I plus plus, simply see out yi, and then, oh, where it has gone, and then endl. Okay, once this has been over, what we'll do is we'll say C out and then some space, so that now we will go for UI. Once this is also over, then we will be printing our exact. So it is U exact. Done, friends. Over. So I think your class is ready. Now inside the main, what we have to do? Simple. We have to create one instance of this class, that is channel flow. So channel channel flow, and let's say it is CF. Now we have, as the constructor was parameterized, so we have to pass the values. So what? So first we have to pass the H. Okay. So let's say that the channel spacing, this one, this H is 0.01 meter. Okay. So it is 0.01. Okay. Where it is writing 0.01. Now it is okay. Now then once this is done, then it is viscosity, then pressure gradient, then epsilon. Okay. Then comes the viscosity. Let's say it is 0.001 Newton second per meter square, and then the pressure gradient. So let us say that the pressure gradient is minus 1000 Pascal per meter. Okay. So it is minus 1000. Okay. And then comes the converging criteria, epsilon. What I'll do, I'll start with 0.1, very poor convergence criteria, and then I will show you that how this particular thing can be made better if I increase the convergence rate. Okay. Once this has been done, so you have created your object, then after this you have to solve it. So you have to call this particular numerical solve. So I am thinking that I have written it correctly. Numerical solve. Numerical solve. Once this has been done, I should also have my analytical solve. So this is where it is. Analytical solve. Let me copy. Okay. Once this has been done, I'll simply display the result. So this is the one, and that's it. If I might have written it correctly, I'm thinking that I have written it correctly. So the program should run. So let us see whether it runs or not. Oh, it ran. But what is this? Why it is? Have I done something wrong here? Because this is okay. This numerical one is, and this is analytical one. This is okay. But why the numerical results are not coming good? Have we done something wrong in the analysis? Now this is something which you have to be very cautious. In this particular solver, what we have done is, first let's check the boundary condition. It is 0 0. Okay. Then we have taken error, and error should be as much as possible in the starting, otherwise it will not go into the particular loop. So you can also, if I run it now, you can see that iterations. So total iteration 1. So this should be as large as possible. So let us take 10, huge number, and now I'll run it. Okay, now it has given some result. So this is my y, this is my numerically obtained result, and this is my analytical exact result. So let us do what? Let us transfer this to Excel to see. So this is my y, okay, and this is my basically what has happened? Nothing. And this is my numerical result. So this is U numerical and then U analytical. So this is my U analytical. So let us do what? Let us write here. One more thing. I'll create some insert. Oops, sorry. So insert and then also one. So what is this? This is for a tolerance of 0.1. I'll also increase the tolerance limit or convergence criteria to 0.001, and then we'll also compare it. So what we'll do is we will create one empty plot and select data, and we'll adding the data in the x. So if you look here, this is my x-axis for that particular table. In reality it is y. So what should happen? So velocity should come here, because with every y I should be in a position to plot, and I've told you na that the variation should come out as parabolic. So let us see whether it is coming or not. So where is the Excel now? So first let us select the data. Again I'll do it. Select data. We'll add. First we will be y-axis and we will be writing numerical, and then the y-axis. Okay, and here friends, what I'll write, u numerical un for 0.1. Now this means 0.1 tolerance. Okay, now we'll add another one. X-axis, again it is analytical, and I'll write u ana, and y-axis is my y. Okay, I think I have done it correctly. So if you look now, let us bring the legends also, and let us do what? Analytical we will write dot, and numerical we will write by we will draw by a curve. Okay, so we'll change this style. The analytical we will scatter, and analytical will be scatter, and the numerical will be my line. Now you can see friends, from here you can very well appreciate the fact, or if you do what? You can 0.01. Now you can see between the channel the flow variation is parabolic, exact parabolic, very good, but the analytical results are slightly more here in comparison to the numerical result. And now it is clear to you why, because of the tolerance level. So what we'll do now is we will change the tolerance level in the program. So where is the program? So here I wrote the tolerance I have supplied as 0.1. Now I'll do what? I will make it to 0.001. Okay, so I'll now write it as 0.001. So if I run it now, so this is my numerical result for 0.001. So if I bring it here, so it is, let us copy and paste it here, and this is 0.001. And now we will insert this also. So add, this is u numerical for 0.001, and the x-axis will be velocity, and let us copy till this point, and the y-axis will be this one, and okay, okay, and this is 0. Okay, and this, let us change the color. Let us make it red, so that it becomes very easy for you to understand it. That's it. Now you can see what? Now you can very well appreciate the fact that as you increase the tolerance, that means as you basically increase the tolerance means as you reduce the error further difference between the exact and analytical, you reduce it further. So you will be coming very close to the analytical results. And that is what we call as Hagen, not Hagen, it is, I think, workflow plane. This is plane Pausili flow in fluid mechanics. And now you have done it. Congratulations. You have solved, you have written a class for a real engineering problem. Okay. So I think you must be in a position now to handle such type of problems even numerically. You should be in a position to write classes even for complex numerical problems also. So that's all for this particular lecture, and in the next lecture we'll come up with another problem with we'll solve one more, we'll write one more class for some difficult to handle problem, and let's see what happens in the next lecture. Thank you very much for watching this one. Take care.